Hello, good morning, Avinash, Atul, Atira, and Realme, 5Y, Manoj Babu, Pranav, Akash, Aman, Pranav. So,
Good morning, sir.
good morning. So it is nice if everybody turns their videos on, but
Good morning, sir.
if you can't turn it on, then that's okay. I mean, but if you can, then it is nice. We have we can see each other and
Good morning,
say good
sir.
morning and say hello. Who is that? Real me?
Sir Vipul.
Vipul. एक second, Vipul. Better हो गया. No, Aman, that is fine. I understand. Network is not that good for many people. So if you have difficulties with that, that's understand. So, see. Good morning, YouTube viewers, Chinmay and Ritik. Chinmay, I hope you're doing well and you have recovered fully. Or to all of you, I hope you are all keeping safe and protected. Winter is here, and I don't know if any of you have watched Game of Thrones or not, but okay, so let's see. So I finally have a decent writing tablet again at somewhat expense to me, actually to the institute, but since the institute pays my salary, I mean, it's thanks to them only, right? So yeah, we'll definitely have a much better experience going forward. So you will see now. Right, much better, I think, than previously. Start the recording.
Yes, sir.
Yes. Right. Okay, so good morning, everybody. Thanks for coming to our today's class. Is the 44th class in quantum mechanics. So in the last class, I started talking about Ehrenfest theorem and correspondence principle, and I explained. So should just tell me, should I orient? Is this better? Is this better or
yes, sir. Yes, sir. This is definitely better.
Yes,
better,
sir.
right? So in the last class, I started talking about Ehrenfest principle, and I explained how the de Broglie wavelength plays a role in determining whether a system displays quantum mechanical behavior or not. And as an example, I discussed the Davison-Germer experiment, right? And which showed that neutrons have a wavelength, they behave like waves, right? So the Davison-Germer experiment verified the de Broglie hypothesis. And this can be this concept can be made more concrete in terms of something known as the correspondence principle, which says that in the limit of large quantum numbers. So what is large quantum numbers? So for example, the mass of an object, right? If you think of the mass, if you think of all of the elementary particles, electrons and protons, which make up anything, right? So you start from a vacuum. A vacuum is just empty space, right? And like in the harmonic oscillator, you start from the zero state, the ground state, right? And then how do you get the excited state? You act on the zero ground state with some creation operator, right? A dagger. So similarly, you think of an empty space as the ground state, okay? And technically, it's not really quote unquote empty. And then you act on this, ground state with some creation operators. And when you do that, you get an excited state, and that excited state corresponds to empty space plus one particle. That is the interpretation of that excited state. So you can think of any object, right? Like an atom, let's say a hydrogen atom, which consists of one proton and one neutron. You can think of it as being created from the vacuum by the action of one creation operator, which creates an electron, and one creation operator, which creates a proton, right? See, you can think of something like this, for instance, so that you have a ground state, which is your vacuum. This is the right, and then you act on it with a creation operator for an electron and a creation operator for a proton, something like this, let's say. And this leaves you with a state which contains a proton and an electron, right? And it's a tensor product state because you have two particles. So you can think of this roughly as, let's say, something which will give you a hydrogen atom, right? Or at least the components of a hydrogen atom. So similarly, excuse me, one second. Similarly, one can consider anything, for instance, an object made out of n particles as being created from the vacuum. Let me put this on. So you can think of any object consisting of n particles, right? As corresponding to some state, something like this, ket n. And you can think of ket n as being created out of the vacuum as by action of some n creation operators, right? So the correspondence principle says that so this n becomes a quantum number, right? Right? So, and this n would be proportional to the mass of the object, for instance. So if you consider something like a bacteria, right? Bacteria consists of, and you compare a bacteria to right, you have a something, you have a bacteria and you have a hydrogen atom, let's say. And you ask what is this quantum number n for these two. So for a hydrogen atom, n would be 2, let's say. And for a bacteria, what would n be? N would be something very large, right? Because a bacteria would contain billions of, millions of hydrogen atoms, right? And other atoms also. So n would be very, very large, right? Let's just say very much larger than 1. So according to the correspondence principle, what we have is that when the systems at large quantum numbers behave classically. So if you consider this bacteria is much more likely to behave like a classical object than a hydrogen atom, right? And this is also what we observe more or less, right? Another example is this, that if you consider just a simple harmonic oscillator, and you consider a harmonic oscillator in a highly excited state, so let's say n is equal to 100, and then you make a plot of the probability density. So this is the x, and this is p of x. So I guess this would be x is equal to 0, and this would be going towards plus infinity, and this would be going towards minus infinity. And this would be p of x, the probability of finding the particle at a certain point, right? The probability density. So when you plot this probability density, you would get this, what do you call it? This line, the wiggly line. And you can make a probability density plot for a classical particle, for a classical harmonic oscillator. This is for a classical simple harmonic oscillator. So how to do this is shown in the notes that I shared with you on coherent states. You can read that if you are interested. Okay, it's optional. And you can see that these two roughly match, right? Even though the quantum state has oscillations, the overall amplitude of the quantum state behaves roughly like that of the classical harmonic oscillator, right? And this, so this is the correspondence principle, which says that systems at large quantum numbers behave classically, right? And then you have Ehrenfest theorem. Ehrenfest theorem says that Ehrenfest theorem is a theorem. It's an actual, right? It's not like an approximate statement. It says that if you take any particle moving under the influence of some force, right? And you write down, so how do I describe the quantum system? According to Schrodinger's, so for what I would do is, I would write down p square by 2m, the operator, plus so this is the kinetic energy, and then I would write down the potential energy part, right? So this is the quantum Hamiltonian, right? So the classical Hamiltonian is what? P square by 2m where P and X are just the numbers, right? They're just numbers. So if you want to get the quantum Hamiltonian, what do? You replace them with the operators. So the quantum Hamiltonian we can solve, let's say we can solve the quantum Hamiltonian, right? And when we solve it, we get some eigenstates. And eigenstates would generally be labeled by the energy or some other quantum number that is this K, right? So these are the eigenstates, and K is the index. K could be anything. It could be the energy of the state. It could be the position. It is some quantum number. And what Ehrenfest theorem says is that if you look at any state, right, of this system, so an arbitrary state of the system, how would you construct an arbitrary state? You would take superpositions of these eigenstates, right? This is an arbitrary state. So you would, you know, I mean, because you are in a, again, always remember, quantum states are, what are they? Anybody? What are quantum states as mathematical objects? This you should remember, like, you know, part of your daily prayers. Vipul, what are quantum states?
Superposition of the eigenstate. Have written down in the superposition of eigenstate.
I mean, as a mathematical object, what is a quantum state?
Wave function.
Yes, but that wave function is what sort of mathematical object? Is it a number?
Probability distribution.
Vector.
Probability distribution you get from the quantum state, right? By taking the inner product.
Vector.
What is the,
Vectors.
Vectors, absolutely right. These are vectors. Right? Always remember this. Quantum states are vectors, right? So these are what? These are the basis vectors. So if you want to write down any vector, you take the superposition of the linear combination of the basis vectors, right?
Yes, sir.
So then, so as an example, if you are working with in the position representation. So in the position representation, what are your eigenstates? Your eigenstates in the position representation. These are the eigenstates of what? Of the okay, sorry about that. Of the position operator, right? Is the position operator a Hermitian operator?
Yes, sir.
Right. So X is a Hermitian operator. So what do we know about Hermitian operators?
Eigenvalues are real.
Eigenvalues are real. And what do we know about the eigenstates?
Are orthogonal.
They are orthogonal, but also
The eigenvalues has to be different for it to be orthogonal.
Right. No, that's fine. But if you look at all of the eigenstates of a Hermitian operator, what is the property they satisfy?
They form completeness.
They form a complete basis. This is the very important, right? This is very important, right? Complete basis of the Hilbert space, which is this fancy curly H. So these eigenstates, these are the eigenstates. This is the operator acting on the state. This is the eigenvalue. So you can write any state as a superposition of these eigenstates, right? Like this. So this should be X. And now, because X is a continuous variable, this is an integral. Okay. And what is Cx? Cx is the coefficient, right? So this is a vector. Right? So, and what do we normally write C of X as what? As psi of X, right? This is what we mean when we say psi of X. Psi of X is the component of psi, right? Along the direction ket X, right? So at each point along the real line, you have a single vector, right? So Ehrenfest theorem says that if I look at for any state, psi, right? So how do you specify a state psi? When you want to say that I have a certain state, what is the data associated with that state? What is the data associated with any vector? How do you specify a vector? Anybody?
It has some magnitude and direction.
No, but
The components along different direction.
components along the different directions, right? So what is psi of X?
Its component along x direction.
Exactly. And by X direction, please keep in mind, I don't mean X direction does not mean this, okay? What is X direction? X direction means at each point along the real line, you have a point X, right? So X direction means ket X direction, the direction of this vector. So you think of this as a vector direction. And this is another direction. These are different directions, right? And they are orthogonal to each other. They are all perpendicular to each other. It doesn't look perpendicular in the picture I've drawn, right? So these are vectors, like you have to think of it a little bit abstractly, right? So this is, let's say, ket X. This is ket of X prime. and they are orthogonal to each other, right? But this is not in real space. This is right. These are abstract vectors. So in order to specify the state, you have to specify all the components of the state, right? All the components of the vector. So you have to give psi of x for each point along the real line, right? So when you say that psi of x is the state, that is what you mean. Because you know what psi of x is as a function. Let's say you know that psi of x is this value at x1, this value at x2, and so on. Okay. So Ehrenfest theorem says that for any state psi, this full state psi, and whether you say psi or whether you give the function psi of x, right? They are the same thing. They represent the same state. But always keep in mind, this represents the full state. Psi of x is the component of psi at x. You should think of it like that. And if you think of all the set of values of psi of x, right? All of the values of psi of x, that constitutes your total state. So this is x. This is psi of x. So you consider all of the values. This is equal to a total state. Okay, I'm emphasizing all of these things a little bit because I think some of these concepts have not like gone into, have not percolated into your understanding. That's why I'm emphasizing these concepts. Okay. So, but we will often refer to just psi of x as the state. Okay. This is what you should always keep in mind when you read something like Zetli or something which doesn't use the Dirac notation. So psi of x is the state, and Ehrenfest says that for any psi of x, that means for any function, right? As long as that function, what is the requirement for a state to be a physical state? Anybody remember what is a physical state? Is any function allowed?
It should be finite as x tends to, it should tend to 0 as x tends to infinity.
No, not, yes, but
It should be normal.
more normalizable. Right? Normalizable. So you can have a state which goes like e to the x. Okay. Let's say it goes like e to the x here for x is less than 0. That's fine. As long as it doesn't go like e to the x for all x. Then for, let's say for x is greater than 0, it can go like e to the minus x. Something like this. Such a state would be normalizable, right? Normalizable means there is a finite area under this curve. So Ehrenfest theorem says that for any such state, if you look at the expectation value of the operator x, and you take the time derivative of that expectation value, it is equal to this thing on the right hand side. So what is the meaning of the expectation value of x? So I have some state, okay? Let's say this is my state, okay? And again, when I write psi of x, keep in mind psi of x means everything, all of the values of x, right? So for such a state, what is this expectation value of x going to be? What is the mean value of x going to be? The mean value of x will be something over here, right? Because this is the region in which the amplitude is maximum, right? What is the mean value of x? If you want to remind yourself, how do you find the mean value of an operator? Like this, right? This is how you find the mean value of something, right? And in terms of this, and this is in terms of the components of psi, right? And then x operator acting on psi of x gives you just the number x, and so you will get x bar, or the mean value of x is this quantity, right? So where psi of x is a maximum, where the maximum probability is, that is where this number will be maximum. You are most likely to get this number, right? So most likely you will have something like this as 1 second. At this point would be your x. Yeah, question.
सर मेरा क्वेश्चन ये है कि समटाइम्स एक्सपेक्टेशन वैल्यू ऑफ एक्स एंड पी 0 होता है, तो इसका मतलब ये है कि फोर्स
So it's fine, right? Zero just means zero is also a location, na?
बट सर अगर अनफेस्ट थ्योरम देखें तो सर इसका मतलब कि हमारा फोर्स 0 है फिर?
नहीं. Ehrenfest theorem says that force, classical force, first of all, what is the definition of the classical force? कैसे लिखते हैं? F is equal to
m into dp by dt.
And in terms of the potential,
Yes.
this is from the acceleration, right? But if you have a potential energy
minus del v.
minus gradient of v of x, है ना? Is equal?
Yes, sir. Yes, sir.
So this is the gradient, na?
Yes, sir.
Right? And what is a? A is the rate of change of x.
Yes, sir.
Second rate of change of x.
Yes.
So the value of x is not important, right? It's the how that value of x is changing. Right? So if you have to write down the quantum version of the force, then this force will also become an operator. acceleration will become an operator, potential becomes an operator. So how do I write acceleration as an operator? Acceleration is, so first of all, I have x. X is my position operator. Then what is my velocity operator? My velocity operator is dx by dt. Velocity operator tells me how my position operator changes with time. Then my acceleration operator will tell me how my velocity operator changes with time. Okay. So
Yes,
in
sir.
order to calculate this quantity, in order to calculate the rate of change of an operator, which is the time derivative, right? How do you do this? Using the Heisenberg picture. Okay. So as an example, remember, if you have the state at a certain time t, right?
Yes, sir.
And you have the state at some other time t naught at an earlier time. So t naught is less than t. Then how are these two states related to each other?
Sir, e के power minus iota h cut upon e1 into t.
Right?
Yes,
What
sir.
is this h? What is h hat?
Hamiltonian, energy operator.
H hat is what?
Energy operator, sir. Yeah, energy.
Hamiltonian, na?
Yes, sir.
ठीक है?
Yes,
Now,
sir.
how do you write this in terms of this wave function notation, in terms of psi of x? So psi, remember that psi we said, and I'm using this sign, this equal to sign with 3 bars. What does this mean? This means equivalent to, okay? This is different from equal. This is equivalent to, meaning you can, they represent the same object, but it's not the same thing, okay? So psi is represented by this psi of x, right? And then what is psi of t? Psi of t would be this guy, right?
Yes, sir.
Psi would be a function of time and position. Equivalence, very important. Okay. Now, how do I evaluate a quantity like this? This exponential minus I. Okay, so let's just write exponential of any operator. Exponential of any operator acting on psi. How do I write this? How do I evaluate this? Exponent of any operator can be expanded as a power series, right?
Yes, sir.
So if I say exponent of O acting on some state psi, I can write that as acting on the state psi. Okay. This
Yes.
I can write as 1 acting on psi plus O acting on psi plus O square by 2 acting on psi and so on. Okay.
Yes, sir.
Screen is big enough or I'll make it bigger? I don't know.
No,
Now-
sir, सही है.
Now consider that this psi is an eigenstate of this operator. Okay. Then, so we will write psi as some k, where k is the eigenvalue. We label the state psi with the eigenvalue. Then what happens to this expression? This expression now becomes one acting on psi of k is just psi of k. O acting on psi of k will give me what? K times psi of k. O square acting on psi of k will give me k square by 2 factorial psi of k. Now I can write this as 1 plus k square by 2 factorial times psi of k. Fine.
Yes, sir.
And what is this? What is this expression?
Exponential e के power k e के power k.
To the power k.
Eigenvalue.
Now this is just a number, right? Now this is just a number.
Yes, sir.
Which becomes a C number. It's no longer an operator. So e to the power O acting on psi of k becomes e to the power k acting on psi of k. This was some complicated operator acting on psi of k, right?
Yes, sir.
And now I have written it as just one number acting multiplied by psi of k. So if psi of k is an eigenstate of O, then it is also an eigenstate of e to the O. Okay. Now so I hope that this is clear. Okay, this is a simple. I'm taking this class a little bit slowly. This is more of a remedial class. Think of this as a tutorial class where I'm covering all the various things which might not be clear, the very basic concepts. Okay, so now this is for an eigenstate. Okay, now if O is Hermitian, right, then psi k, this set of states psi k form a complete basis, right? Or complete set. Okay, so I can write any state psi as this Now this state psi does not need to be an eigenstate of O. Okay. But now I can use this result to calculate what happens. So I take e to the, so I will write this, let me write it as exponent A, like this. Exponent O acting on psi, where psi is any state. Not necessarily an eigenstate of O. Okay. Then I substitute this expression in here. What do I get? Exponent O multiplied by sum over k, ck, psi k, like this, right? Let me copy it to this page. This I can write as summation of k. I can take this thing into the summation sign, let's say, right? And c of k is just a number, no? So I can put c of k over here. Do you guys have a class at 9 o'clock, by the way?
Do so.
No. So I hope it's okay if I take another 10 minutes or so. Is that okay with everybody?
Yes, sir.
Do so.
See, I'm going a little bit slowly. That's why the class is a little longer. But the reason I'm going slow is because I want everybody, I want every single person to understand these concepts. And these concepts they are not difficult. But you just need a little bit of patience and a little bit of time. Okay? They are not difficult concepts. It is all just linear algebra. Now, this exponent of O acting on psi of k, do we know the answer to this?
EK psi k.
EK psi k. So what is the result of this exponent of O acting on psi? It is summation of ck ek psi k. And once again, I'll put a nice box around this result. This is a very important expression. Right? Now, why have I gone to all this trouble? Because of this. Right? So now let me returning to the time evolution of the state. So the time evolution is given by this. What is this? This is exactly the form of this, right? There is some operator. It is acting on some state psi. What is the operator? In this case, it's minus I delta t h bar by h. Okay. Is this a Hermitian operator? First of all, we have the Hamiltonian. Is the Hamiltonian a Hermitian operator?
Yes, sir.
Yes, sir.
Hamiltonian is Hermitian, right? So if I take I times H, is this Hermitian?
No, sir.
No, this is anti-Hermitian, right? But that's okay,
Yeah.
because even whether you have Hermitian or anti-Hermitian operators, they will both satisfy this. Their eigenstates will be a complete set. Okay. So the point is that now I can write down my state psi as a superposition of the eigenstates of the Hamiltonian. Okay. So I will write it like this. My Hamiltonian has some eigenstates with eigenvalues E, because E is the energy, right? The eigenvalue of the Hamiltonian. So my state psi, and now I will write this as psi of t. But psi of t in the Schrodinger picture. So in the Schrodinger picture, my basis states don't change. My basis states are independent of time. The coefficients of those states. So I'm sorry. In the Schrodinger picture, my states are functions of time, and the way I write this time dependence is I put this time dependence into the coefficient. Okay. So now I can see, I can substitute, I can write down what this expression is going to be. So psi of t naught, what is psi of t naught going to be? It is going to be C of E at t naught sum over all the energy eigenstates. So psi of t is now exponential of minus I delta t by h bar, operator h acting on psi of t naught. Again, now I can write this as exponential. So again, let me expand this state in terms of the eigenstates. So this will become C of E at t naught exponent minus I delta t by h bar hat h acting on psi of E, which is equal to summation of E C of E t naught exponent of minus I delta t by h bar. And now what will I replace this h operator by? I can just write down the eigenvalue E inside the exponential. Right? So I know by now most of you are tired and bored, so I won't take too much of your time. So what is the relation between the two states? The one state has coefficients which are given by C of E at time t naught. The other state has a coefficient which is given by C of E at a time t. So what is C of E at a time t? It is C of E at a time t naught multiplied by exponent of minus I delta t E by h bar. So the coefficient just changes by a single phase. This is a complex phase, right? And what is delta t, by the way? Delta t is equal to t minus t naught. Okay. Now, all of this is in the Schrodinger picture. In the Schrodinger picture, my state is changing with respect to time. But I want to ask how to write down the time derivative of an operator. So to answer this question, what I have to do is returning again to time derivative of an operator x. So how do I write down d naught by dt? What is the meaning of this expression? So first, let me write down. So if I have an operator at some time t, let's say that O is a function of time, okay? Then I can write the expectation value of O will also become a function of time, right? And what is this quantity? This quantity is psi of t O psi of t. Is anybody still there? Anybody is still
Yes,
awake?
sir.
Yes, sir.
Now, this expression can also be written as psi of t naught. ठीक है? What is, now we remember what is psi of t. Psi of t is this expression. So this can be written as psi of t naught exponent I delta t by h bar. Okay. Now there is no minus sign here. Why? Because I'm looking at ket of psi of t. So when I look at the ket, of this whole thing, I get ket of psi t naught times complex conjugate of this. Complex conjugate will give me a plus sign over here. Multiplied by the operator O multiplied by exponent minus I delta t by h bar. Acting on what? Psi of t naught, right? Now, psi of, so this expression you can write as psi of t naught OT, psi of t naught, right? So in other words, what we have done is this whole thing, right? This whole thing we are going to now write as an operator which corresponds to the operator O at a later time t. So O of t, operator at a later time t, is given by this expression. See, one thing is that now I can write nicely on this tablet now. So I'm also enjoying a little bit teaching because the screen is big and I can write without any hassle. So this is the time. This is how you take an operator and evolve it in time. Okay. So now we can ask what is x of t. X of t will be exponent of all of this, and I will just call all of this something. I'll just call it u, acting on x at time t naught, exponent of minus u. U is equal to I delta t h hat by. Okay. And now I can calculate the time derivative of x, of this operator x. By taking the time derivative of this thing on the right side. And I should write this as exponent of u as a function of time. This is very important. So this is u as a function of time. Now I can calculate the derivative. To calculate the derivative, I get three terms. I get the derivative of this, derivative of this, derivative of this. And when I calculate these three terms, what will the answer be? The answer will be, I will get this expression. And there will be another term which is this partial, if in this case the operator O, or in this case the operator X, has an explicit time dependence. So I'm going to leave this as a problem for you for homework number 5. So you have to start from this expression with u is given as this expression and calculate dx by dt and show that for any operator, not just for x, you have to take the time derivative of this whole thing. You have to show that this is equal to minus I by h bar, or you can write plus I in h bar. You have to show this. Okay, I'll leave this as a homework problem for you.
Sir,
And the
this
second-
will be in homework 6, I guess. Homework 5.
That's right. You're right. You're right. Homework 5 is due tomorrow. So homework 6. So then problem number 2. Put O is equal to X. Okay. And put H is equal to this Hamiltonian for a harmonic oscillator. and then you calculate dx by dt and also dp by dt. Right? And you can do this because you know how to calculate the Hamiltonian of h and x, right? For a harmonic oscillator, you remember? So you can do this calculation. It's also in big red letters. Put it a little bit nicely. Okay. Questions?
सर वो लिंक शेयर कर दीजिएगा होमवर्क 5 का जो मूडल पे
क्या चीज?
सर वो होमवर्क 5 के लिए जो लिंक शेयर कर दीजिएगा मूडल पे.
Oh, okay. For submission, ठीक है. I'll do that.
सर जैसे हमने अभी xt निकाला तो this is an expression of exponent to the power something positive and to something into exponent to the power something negative. तो वो मतलब
One second. The positive and negative is I'm just making a choice. Okay, I can write this as negative and this as positive. It doesn't matter. ठीक है ना?
like won't they be cancelling out?
नहीं, they will not cancel out. This is the whole point. This is the whole point. This is the crux of the matter. If they cancel out, then there is no time evolution, na? And the reason they don't cancel out is because this u and this x, it does not commute, na?
So like when
See,
we were calculating.
See, one second. Let me give you an example, okay? You have two operators A, B. And you know that A, B don't commute with each other, okay? Then I write this exponent of A times B. Okay? Is this equal to B times exponent of A?
No sir.
No, na?
No sir.
So
Got it.
okay?
Yes sir.
That is the whole point. Now, if you have an operator which does commute with B, right?
Yes sir.
So if you have an operator which commutes with the Hamiltonian, okay? So if you have some operator O such that the operator O commutes with the Hamiltonian, then what can we say about the operator O at a certain time t?
Its state doesn't change like over the evolution of time.
The operator doesn't change.
Probability doesn't change यानी sir.
No.
Probability
Keep in mind we are talking about the operator. Probability comes when you talk about, you have to specify the state also, no?
Yes, sir.
An operator, it doesn't depend on which state you act it on, right? Operator is like the machine. Okay.
Yes, sir.
So if you have an operator which commutes with the Hamiltonian, then that operator is time independent.
Yes, sir.
As
Sir,
an
also
example,
called constant in motion, system in constant in motion.
exactly, a conserved quantity. Then if you take the expectation value of this will be a conserved quantity. Or constant of motion. Okay, we can look at a very simple example for a free particle. For a free particle, which means the potential is 0, right? And the Hamiltonian is what? P square by 2m.
Yes, sir.
Now, if I look at the momentum operator, P, does this commute with the Hamiltonian?
Yes, sir.
This is 0 because this is P square. No, P will commute with P square. So this tells me that for a free particle, the momentum is a conserved quantity. It's a constant of motion.
Yes, sir.
Which is what we expect, no?
Yes, sir.
Right? Because you have a free particle. Free particle means it doesn't have any force acting on it. If there is no force acting on it, then the momentum of the particle should not change. Okay?
Yes, sir.
So I'll stop here for the day, and today was, I guess, a little bit of a longer class than normal. 6 pages of notes as opposed to the normal 4. First, let me see any questions on YouTube. Okay, good. No questions on YouTube. All right, I'm going to stop the recording and the streaming.